Which protection principles are available to detect short circuits? Let's look at this picture. Imagine we have a line and we have a protection relay, maybe on both ends of the line. They can measure the voltage and the current. And now, how can we detect that there is a short circuit on the line? And there are basically three principles available to do that. One is just looking at the current. It's quite obvious. If you have high current, it looks like a short circuit. That means the amount of current is an indication for a short circuit. And protection based on current, on only the current, is called overcurrent protection. We will look at that a bit more in detail later on. The next one I would like to mention is protection which is based on the impedance. That means we measure the impedance. To get the impedance, we have to measure the voltage and the current. And if we divide the voltage by the current, we get the impedance. And we will also see, based on the impedance, we can make a decision, is there a short circuit on the line or not? And protection based on the impedance is normally not called impedance protection. It is called distance protection, because the impedance is somehow a criterion for the distance of the fault. And the third principle is based on a current difference. That means we measure the current at two different locations and compare them, and from that we try to find out, is there a fault on the line or not. And that principle is called the current differential protection. That means we have three different principles: overcurrent principle, distance principle based on the impedance, and the current differential to detect short circuits. I mentioned already in the beginning, we have also other types of faults, and to detect them, we need other principles. We can look at the voltage. We have to detect over voltages, under voltages, also the rate of change of the voltage, and the current is sometimes required. We can measure the power, apparent power or real power, and also the frequency is used as a criterion, and also the rate of change of frequency. Maybe the frequency, for instance, is often used for load shedding. You may know that normally the frequency is very close to nominal frequency, 50 Hertz or 60 Hertz. And if the frequency goes down, it's an indication that there's a lack of power in the system. And so what we often have in the systems is that if we see the frequency goes down, or we have a certain rate of change of frequency, we disconnect loads to stabilize the system. So these criteria here on the bottom are used to detect other faults. We will now in the next slides focus on the detection of short circuits, and we will start with overcurrent protection. That means our device only measures the current, and the job of the device is now to detect, is there a fault, a short circuit on the line or not? How can this be done? Imagine we have a certain range of currents, and what I indicate here in green is the normal operation. That means in normal operation, we measure a current between 0 on the left-hand side up to a maximum load current. And then we have a range of short circuit currents. Typically, when you engineer your substation, you calculate the maximum short circuit current which may occur, that is always required to dimension the cross-section, for instance, of the cable. That is the maximum current at the right-hand side, but we are, of course, not interested only in short circuits with the maximum current. We must also take into account short circuits where lower short circuit currents are flowing, because there is some fault resistance involved, or not all generators are operating, or whatever. And with these considerations, we end up with a minimum short circuit current we want to catch. And if we now see that we have a gap, as in this diagram, between the maximum load current and the minimum short circuit current, then we can make a setting somewhere in between and can say, okay, in this gap, I define a limit. And as long as the current is below this limit, I consider this as normal operation. And as soon as the current is above that limit, I consider that as a short circuit and will react on that. Important thing in this context is, what is the maximum load current? And that is in many cases not so obvious. Imagine you are behind the transformer, then you can say, okay, the maximum load current is the nominal current of the transformer. But is that okay? Imagine you can overload a transformer. That means you can have cases where you have a short overload, and if you set your limit directly to the rated current of a transformer, as soon as you have a slight overload, our protection will see, oh, it looks like a short circuit, and will trip. And that's not good. That means you must make up your mind, what is really the maximum current you will see without a short circuit? And that is often not that easy. Remember, for instance, one critical situation. You have an overcurrent protection, and behind this protection, or this protection looks into a distribution system which supplies a number of streets in your city. And you have this thing out of operation for maintenance or after a blackout or whatever, and you are in a city with very hot temperatures. That means you have a lot of aircon. And your maintenance or repair work takes 2, 3, 4 hours, sun is shining, all the buildings heat up, and now you reconnect power. You are happy, your repair work is done, you reconnect power, and then at the moment you reconnect power, all the air cons start running at the same time, and you get really a high current in the beginning, which slows then down a bit. But if now your setting is too low, with this high current you come above your setting and you will trip again. That means you won't get that system into operation again. And that means if you think about the maximum load current, you must take into account such considerations and must add a certain security margin there that you don't get this problem. The other thing you also have to take into account there is you have to look into the future, because you calculate your setting when you install the device, but you don't want to reconsider the setting every month. That means you must have a setting which is also valid after some years, when maybe the system has been extended later on. Also, that means you have to look a little bit in the future. But important thing here is what you can see from this diagram. You can only catch faults, you can only detect faults where the current of the fault is higher than this maximum load current plus a certain security margin. With that, you cannot detect faults with a very low current. That's not possible with this principle. That means if that can be applied, we can detect fault. But remember, detection of fault is one story. We also have to be selective. Detection of faults means the current is that high, there must be a short circuit, but we still do not yet have the decision, is the short circuit on our own line or is it on the next line? That means the topic of selectivity is not included here. We will see later on in the second part of this webinar that we need some time delays to get selectivity. But basically, this principle is widely applied. You have it in fuses, and here in our field, you have it in protection relays, overcurrent protection, and there we have to distinguish between two different types, inverse time overcurrent protection and definite time overcurrent protection. We will look now a little bit into these different types, how they work. So how does an overcurrent protection look like? Let us start with the three phases of our protected line or cable. They are shown here. And now we measure the current, only the current, by using this red current transformer, and we connect this current transformer to our protection relay. I draw here parts of a protection device. You see here an input transformer. That's a measuring input, the connection point where the relay measures the current which comes from our current transformers. Then we have a shunt, A to D conversion, some algorithms who calculate the current. And then somewhere in the digital system, we have the amount of current we see. And with this current, we go into this blue block. And that gives us a signal if the current is above our threshold limit we just discussed in the previous slide. And it also takes a time delay. That means the behavior of the relay is mainly affected by this blue block. And in this block, the user has to do some settings to adapt that to his system. If the block issues a signal, it then goes to the circuit breaker and will trip. This shows just one phase. We always have three-phase system. That means we must multiply that by 3. And we do here on the right-hand side an OR connection. That means if we see a fault conditions in at least one of the 3 phases, we will issue a trip command so that we can detect all types of fault. Now let's look a little bit more into these blue boxes. What is inside there? And that is shown on the next slide. As I already mentioned, we have 2 types of overcurrent protection, and they can be distinguished by looking into these boxes. That means these boxes have a different characteristic. That means a delay time depending on the current they detect. And this characteristic is normally plotted in such a diagram that you see here on the right side. The horizontal axis is the current we measure, and the vertical axis is the delay time. And what you see here is a certain range of current from 0 to the setting value. This is the setting value. This is the load area. You see that would be the nominal current, maybe of our transformer or whatever. We have a certain security margin. And as long as the currents are somehow in this load area, the trip time is infinite. That means we have no trip. As soon as we are above the setting limit, then we start our timer, and then we will issue a trip if this condition remains there for a given time. That means a time which is given by the user. That means this characteristic has basically two setting values. One is the current setting and one is the timer setting. The current setting is derived from the considerations I did on the previous slide. Above maximum load current plus a certain security margin. The timer setting comes from the selectivity considerations we will discuss later on. This type of protection with this defined time as soon as we are above a limit is called definite time over current protection. Another alternative for this block is the so-called inverse time over current protection. There you have, first of all, a similar situation. That means as long as you are in the load current area, you have no trip. Trip time is infinite. As soon as you are above a set value, it means, yes, I detect a short circuit, but then the trip time depends on the amount of current we detect. That means if we are slightly above our limit, we trip with a longer delay time. If we have very high current, we trip with a shorter delay time. That's a typical characteristic you may know from fuses. This is called inverse time characteristic, and we will show in a separate chapter how you can get selectivity by applying these concepts. So either using definite time or inverse time characteristics. That was the overcurrent protection. So remember, second principle, distance protection based on impedance. How does that work? This picture shows just an extract from a meshed system. And of course, in a meshed system, on beginning and end of every line, you have a protection relay with a circuit breaker. What I show here is only one of these protection relays to explain the principle. This protection relay measures voltage and current and calculates the impedance. And now it compares the measured impedance with the impedance of the line. And based on this comparison, it can decide, like in the upper part, if the short circuit is on the line, the measured impedance from the relay to the fault is smaller than the impedance of the line. And if you look at the lower part, where the short circuit is on the next line, it measures a larger impedance, an impedance which is higher than the impedance of the line. Then it says, okay, I see a short circuit somewhere, but it's not on my line. That means based on this comparison, measured impedance against impedance of the line, we can get a decision, fault on the line or fault somewhere else. That means with this, we can get selectivity without any delay times. And that is the advantage of distance protection. I already mentioned it's called distance protection, although it is based on an impedance measurement. That means we also have this blue block in our device. But the content is a bit different. We need as input quantity the voltage and the current so that we can calculate the impedance. You may know the impedance are treated as complex values, unfortunately. That means we have a resistive part, which is drawn in the horizontal axis, and we have the so-called reactive part, which is drawn in the vertical axis. That means if we do one measurement, we get one measured point in this so-called complex impedance plane. And to make the decision, is it on the line or not, we define an area in the impedance plane, and as soon as we measure an operating point inside this green area, we issue a trip signal. That is the principle in distance protection. Third criterion was the differential protection. What is the idea there? Remember, you have a simple line. I indicate here the three phases. I first of all focus just on one phase. You measure the current at both ends of the line, in this case indicated as I1 and I2. Normally, current flowing into the line is calculated as positive. That means if we have in this picture here a current flow from left to right, let's assume 100 amps, I1 would be 100 amps and I2 would be minus 100 amps because it flows against the indicated direction. That means in normal operating state, the sum of these two currents is 0. If we now have a short circuit on this phase, that means a connection from the phase to ground or from this phase to another phase, it disturbs our equation. And that means the sum of the two current is no longer equal to 0 because part of the current flows another way. That means we can use the sum of the measured currents as a good indication, is there a short circuit on the device or not. And that is the differential criterion. In this case, I introduced it just for a single line with two measurements. You can also use it for a multi-terminal line because the principle remains the same. And that is indicated here. That means you draw a circle around the protected zone. The protected zone can be a line, a transformer, a bus bar. You measure all the currents and you sum up the currents. Do that individually for all three phases. And in normal operation, this sum should be 0. And if this sum of the three currents, we call this sum the differential current, is unequal to 0, then it is an indication that there is a fault on the protected line. You may realize in this context, just comparing a measured current with 0 and saying, okay, as soon as it is unequal to 0, there is a fault, is not a good idea. Of course, in real life, we must always compare it with a certain tolerance, with a certain threshold value. That means finally the differential criterion is we calculate the differential current and compare it with a certain threshold. And that is a little bit the tricky thing in differential protection, to define the correct threshold values. But the principle is a very simple thing. And we can apply it, first of all, to lines, as indicated here. We have a line from A to B. We want to protect this line. We want to detect short circuits there. What do we have to do? We have to install a protection relay on both ends. That means one protection relay can measure the I1, the other protection relay can measure the I2, and now, of course, they have to exchange their information because we want to calculate the differential current I1 plus I2, and that's only possible if they exchange their measurements. That means a differential protection, a differential line protection always needs communication between the two or even three devices if we have a three-terminal line. And this communication, and that is important, is part of the protection system. It must be a reliable communication, because as soon as the communication fails or something goes wrong there, this protection doesn't work any longer. Communication is part of the protection. And you can imagine in this field, there's a lot of development going on at the moment. This principle of differential protection is already a very old principle. But nowadays, a lot of development work is going on in the field of communication, so that a lot of development is done there. For instance, discussing the question, can we use a company communication system for this data exchange? What about cybersecurity issues? Is it possible to hack into our devices if somebody gets access to this communication, and so on? That means beside these original really basic protection issues, you get a lot of other issues to be considered in this context. That is the application of the line protection principle, of the differential protection principle to line protection. The next area of application would be to apply that for a transformer. Then we don't need this communication thing, because we are within one substation. We can measure the current on both ends of the transformer. But now we have to take into account a few other things, because on a line, it's easy. If we have 100 amp flowing into the line, there should be 100 amp flowing out of the line on the other side. Of course, in a transformer, it's a bit different. Transformer has a winding ratio. That means if there is 100 amp flowing into the transformer, on the other side, we have a different current. That means we must take that into account to apply the winding ratio. And it's not only the ratio. If you look at a three-phase power transformer, that normally has, depending on the connection of the windings, has a phase shift between one side and the other side. And that also means if we compare the current on one side to the current in the same phase on the other side, we must take into account this phase shift resulting from the connection of the windings. And we also have to think about what happens if we energize the transformer and we have an inrush there. That means the principle, the differential protection principle, can be applied to transformers, also to motors and generators, but we have to take into account a few things to make it applicable in reality. And the third area of application is the busbar protection. Busbar protection, it looks pretty easy. We have a busbar, we have in this case 5 outgoing feeders, and we just measure the currents and sum that up. Always separately for the 3 phases. Often these substations don't unfortunately look that easy. For that reason, I would like to show this example with a double busbar substation. You see here 4 outgoing feeders, double busbar, and every feeder has 1 circuit breaker, 1 current transformer, and every feeder can either be connected to busbar A or to busbar B, depending on the position of these isolators. Or even both isolators are closed in special situations. And of course, we want to apply the differential principle separately for both busbars. That means we want to calculate the differential current for busbar A and the differential current for busbar B separately. And to do that in a proper way, we must take into account the position of all these disconnectors here. That means we must combine the topology information, position of disconnector, with the measurement to apply the principle. That looks pretty trivial in such a small system, but imagine you have a bus bar, maybe you have a triple bus bar, you have 20 feeders. That means you have a lot of wiring and you have a lot of contacts, and you must also make up your mind what is going to happen if one of these contacts are somehow dirty, defective, or whatever, and you get the wrong topology information. How does it disturb the measurement? Because then you may do a wrong assignment of a measured current to a bus bar. And that makes the application of the differential principle a bit tricky in case of the bus bar protection. And you must always have in mind, if something goes wrong in a line protection, you have a wrong trip, you lose one line in the system. It's not nice, but it will not be a very severe thing. If something goes wrong in a bus bar protection, you lose the bus bar, and that means you lose all lines connected to that bus bar. That means with one wrong trip of a bus bar protection, you may lose 10 lines in your system, and that can produce already a critical system state. So with this slide, we are through the 3 protection principles. And in the next chapter, we will look at a very strange thing. We will look at the earth current.